interrupted, decided to pause it at that point. So we have a graph over here, and we can see on the graph that as x approaches 0, if we're coming from this side, it's going down, which means it's going to negative infinity. And if it's going this side, going this way, it's going to positive infinity, which means the limit does not exist. Now, there are times that even a graph may not help you get information, and so this is where we can start using tables. You can put a table together, and at that point what you would do is you would, okay, I need to get to 0, so then the negative side would be at negative 0.1, negative 0.01, negative 0.001. Then you would put 0 in there to identify the limit, and then 0.001, 0.01, and then 0.1. And you would use a calculator to find these values. Now, in class, I'll show you how to quickly get these information. Some of you on the last packet, I was able to do that for you. So on this one here, we get negative 50, then negative 500, then negative 5,000. And on the calculator, it will give you error here. So what you do is you do the one side, and then you approach it from the other side. If the numbers are the same, then you have your limit. If they're not the same, then you do not. Now be careful here, because negative 5,000 and 5,000 are not the same. So your calculator would give you an error, but because this is not the same as this guy's going to negative infinity, positive infinity, the limit then would not exist. So you can just D&E, does not exist. Okay, so let's try another one. This one you don't have the calculator to, or the graph to look at. But if I plug 2 in, I'm going to get 8 minus 1 over 2 minus 2, which is going to give me a 7 over 0. Now remember, when we had 0 over 0, that meant you can do something to the function. Algebraically, do something. But when you get 7 over 0, that's not the case. You need a table or a graph. There's another way you have to approach this. So we're going to go ahead and make a table. And since we're trying to get to 2, I'm going to start with 1.9 and work my way to 2. And on the other side, I'll start at 2.1 and work my way closer to 2. So I got 1.9, then 1.99, 1.999, and then I have 2. Now on this one, you know, if I started way over here, I'd work closer to 2. So I actually want the closest number to 2. So 2.001, 2.01, or 2.1. Now, this is where I want to ask you to recall the very, very beginning of the section that when we were trying to find instantaneous speed, this is what I was using, 1.999. You could have also used 2.001. Then it would have been 2.001 minus 2. Either way, you still would have been divided by 0.001. Okay, so on this one, as I put in negative 58.59, negative 688.1, negative 69.88, and this is going to give me an error. And if I start at 2.1, I get 82.61, 712.06, and 7012. Negative numbers, positive numbers, they're both going in different directions, so again, does not exist. And that is the biggest thing. We can go back to the instantaneous speed and do the same thing. When I was trying to get to 2, I had to do 1.9, 1.99, 1.999. What happens at 2? And then on the other side would be 2.1, 2.01, 2.001. and we get closer, we can see what's going on closer and closer together. Okay. Well, this examples we just did is doing that left and right limits. So this would have been the limit as x approached 2 from the left, and this side would have been limit as x approached 2 from the right. As I got closer and closer to 2 from the right, it got larger and larger and larger, and from the left it got smaller and smaller and smaller. Definitely not going to the same spot. So let's talk about one-sided limits. So here it goes. Sometimes the values of a function f tend to different limits, I'm obviously missing a word here, tend to different limits as x approaches a number c from opposite sides. When this happens, we call the limit of f as x approaches c from the right hand limit of f at c, and the limit as x approaches c from the left-hand limit. Right-hand limit, the limit f as x approaches c from the right. Notice they have a plus sign, because on a number line, here's 0, our numbers are positive over here, negative over here. So from the right of your number would be positive, and to the left of your number would be negative. So in the left-hand limits, the limit of f as x approaches c from the left, there it is, the negative sign. But really all they're identifying is using a number line. And you pick your number, I could have put 10 here. If I'm looking for the limit as x approaches 10, anything that's to the right of it would be the positive. They would mark it as a positive. Those are the right, and the negatives on the other side, because that's how the number line works. I missed one little itty-bitty thing down here. We sometimes call limit as x approaches c f of x the two-sided limit of f as c, distinguish it from the one-sided limits. In all honesty, here's a statement on that one. If it's a one-sided limit, we state it to be a one-sided limit. If we don't state it to be a one-sided limit, then it's a two-sided limit. I will not ever purposely go, oh, we're doing a two-sided limit here. No, that's not what's happening. Okay, so theorem 3, one-sided and two-sided limits. A function f of x has a limit as x approaches c if and only if the right-hand and left-hand limits at c exist and are equal. So the limit as x approaches c if f of x equals L, this is a symbol for if and only if. The limit as x approaches c from the right of f of x is equal to L, and the limit of f of x as x approaches c from the left equals L. Anyways, your left-hand limit equals your right-hand limit means the limit exists. So I can go back to this problem going, the left-hand limit does not equal the right-hand limit, therefore the limit does not exist. Okay, so we want to look at this one here. Find the following limits from the given graph. So I want the limit of f of x as x approaches 0 from the right. So this is 0 from the right, so it has to have a line, has to have a way of getting there. It comes down further and further and further. And our y value, please remember we're looking at y values. Okay, y values. This gets closer and closer to 0. The value of y is 0. Now they ask you, do the limit of f of x as x approaches 2 from the right. Well, here's 2, but I have no way from the right-hand side to get there. So that say does not exist. You have to have a line, kind of like a road. You're driving down a road. If you can't get there from the road, then the road doesn't get you there. Simple. Okay, limit of x as x approaches 2 from the left. Well, here's 2, and on the left-hand side is 1. So if I start at 1, as I get closer and closer to x equals 2, my y value is 4. Then they ask you, what is the limit of 2? Well, since this does not equal this, it's a does not exist. And remember, the left and right limits, they are not equal, therefore we get the limit does not equal. Last one is the limit of f of x as x approaches 3 from the right. So 4 is to the right of 3, so I can start there, and as I get closer and closer to the x value being 3, my y value again is 0. The main thing to remember on here is that whenever we talk about limits, we're referring to the y value. A lot of students will look at this going, well, as x gets closer and closer to 2, they try to go around here because this is 4. But that's the y value. It's okay for the y value to be 4. I want to know, as x gets closer and closer to 2, my y value, there it is. That's my y value. Okay, sandwich theorem, squeeze theorem. They're interchangeable. If we cannot find a limit directly, we may be able to find it indirectly with the sandwich or the squeeze theorem. The theorem refers to a function f whose values are sandwiched or squeezed between the values of 2 other functions, g and h. If g and h have the same limit as x approaches c, then f has that same limit as well. Because remember, they're saying that it is sandwiched or squeezed between the other 2 functions. So on this one here, okay, so they have in symbols. If g of x is less than f of x, which is less than h of x, for all x does not equal c and some interval about c, then the limit as g of x approaches c equals the limit as h of x approaches c is equal to L, then the limit of f, the one that's in the middle, also approaches L. So we can kind of play with that one. We'll do one here in a minute. Like this one here, we'll do the squeeze theorem on this one. Now there is a video, and in class I will probably show you the video, or I'll put it online for you to watch. There's a bunch of videos out there for the squeeze theorem. You don't have to know how to get to the squeeze theorem. Anyways, you don't need the proof. You just need to know how to use it. So keep in mind, the one thing is that when you separate it, it has to be 2 different limits. So this one here, if I look at this guy here, and I'm going to look at my range, because remember, it's that f of c value that we're looking for, which is a y value. This guy here is stuck between -1 and 1. Always is going to be stuck between -1 and 1. However, this guy, if I have a positive x squared, will always be positive. And if I throw a negative in front of x squared, he'll always be negative. So I can actually claim that negative x squared is less than or equal to, and I'm going to leave it blank, positive x squared. And most of you go, oh yeah, because I put in 2, I'm going to get -4 for negative x squared, I'm going to get +4 for positive x squared. Because x squared always gives me a positive value, all I have to do is throw a negative in front, and now it's negative. But this guy here, bless his little soul, is always stuck between -1 and 1. But guess what? X squared evaluated at -1 is 1, and x squared valued at 1 also is at 1. So this guy here is going to, and if I throw a negative in there, there it is, -1 to 1. And it's very, very close to the x-axis. So I can claim here that x squared, negative x squared, is less than x squared, sine of 1 over x, which at the same time will be less than x squared. You do have to prove that this guy here will always be between these 2 at all times. So now all I have to do is my limit. So I need the limit as x approaches 0 of negative x squared. That is equal to 0. And the limit as x approaches 0 of positive x squared also equals 0. Therefore, and yes, that is the symbol for therefore, the limit of, as x approaches 0 of x squared sine of 1 over x must also equal 0. And so we get it to be 0. Now, I can't state enough that you do have to make sure that those values are in between. You can graph this thing and look at it and see that they actually touch when the y values are -1 and 1. That's when they actually touch. And at 0, go figure on that one. There is something else I was going to look, is to remember that we can't just plug and chug. I can't do sine of 1 over 0, because you can't have 0 in the denominator. Therefore, we couldn't have just plugged the numbers in to find out it's going to be 0. That's why what I did is I just kind of pulled it apart and said, well, this part here is what it's going to be trapped in between. It's this guy here. Okay, let's try another example. Well, actually, this is the limit to no, is the limit as x approaches 0 of sine of x over x is always going to be 1. That's the one. Now the proof, that if you ever watch the proof, they use geometry. So the proof on YouTube uses geometry to prove that this works. Okay. Okay, I have changed the homework on this one here. Oh no, this is the homework I changed it to. So this is the homework. Every other odd. So, you can start doing the math, going, oh, there's 46 problems. If I divide it by 4, about 11 problems is all I've given you. So there you guys go. But this is this is a limit to no. And we'll work together on this some more. And, memorize. There's another one that I have to remember, and it has cosine, but I don't have it on my paper, so I'll find that one and give it to you guys as well. Well, good luck on the homework.